reservations in two-way slabs by means of yield lines. This video will deal with cases 11 to 15, and it's about a slab who is on two sides fixed and on two adjacent sides simply supported. This will go about case 14, and case 14 is a centric wall attracting the yield lines. As you can see, we use the 30, 45, 60 degree rule, but more realistic when you have a centric reservation in the slab, the corners of the reservation will attract yield lines. So this rule of 30, 45, 60 is not valid in case 15 and 14. However, the condition is that D3 and D4 must be of a certain size, because if this is too small, you will have completely unrealistic yield lines. So we must take care of this. So we have a rectangular slab with a reservation D1, D2, which is centric placed in the slab, and the yield lines are connecting, so you go from corner to corner, independent of the angle they are making. Then we have the conditions of this case 14 element. Two-way slab means that B must be between A and 2A. Of course, the maximum size of the hole will be within the slab, which is logic. And the horizontal symmetry gives you a relation between D4, D2, and B, and between D1, D3, and A. The sum of all those values will be equal to A, and this one must be equal to different types of centric holes. It can be a square or a rectangle, or like this or like that. So that are the typical cases 14 holes. Now let's calculate the work done by the external forces. So we know it's a summation of 1/3 of the triangles and half of the rectangular elements. So E over Q delta is an equal to, we have 4 times 4 times D3, which is this, D4 times D3, D4 times D3, so in the 4 corners, and then 1/3 because it's triangles, and then what is left over, it's 4 times rectangular, but they are equal. The half of it is equal. So you have D3 times D2, D3 times D2, which is this part. You have it twice here too, and then D4 times D1, which is this part, and it's also here, D4 times D1. So we fill in the different variables, and we got this formula. The work done by the internal forces is the projection on this rotation axis of the yield line is B, and the maximum angle is theta over D3. So you have B over D3 for this line. This line here for the negative bending moment is A times delta over D4. And then we have the 4 corners. In each corner, you can project to this axis of rotation and to this axis of rotation. So you have the length, D4 divided by D3, the angle of rotation, plus D3 divided by D4. That's for the 4 corner yield lines. We fill in the different variables, and we have this formula. D is equal to E, so we can get M out of it, and this is the formulation for M. We will work with no units, so alpha 1 of alpha E is G divided by A, and B over A is alpha. Bearing capacity is defined as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. We select the different parameters and we got this formula in the slides. We notice immediately that alpha minus alpha 2 is here in the formula on this location. This means clearly that B must be bigger than D2, otherwise it will have a negative bearing capacity. But this is very logic. Huh? The hole cannot be bigger than the slab. Same is here, alpha must be bigger than D1. Oh, A must be bigger than D1. The uh, bending moment of the slab without a hole and with a 30, 45, 60 rule, be careful of that because the reflecting yield line is different. And then you have the M0. We define it always regarding the 30, 45, 60 rule. We can now put the formula into a graph. X-axis is alpha, which is B over A going from 1 to 2. And on the Y-axis is the bearing capacity for B1, which is the smallest diameter of the reservation, equals to 0.2. And D2 varies from 0.2 to 0.8. So it is a situation like this. For instance, for alpha equal 1.6, you will see this is reservation is 0.2 by 0.2, which corresponds with that. This is 0.2 times 0.4, 0.2, 0.6, and so on. So you see visually now what type of hole this is and where this graph can be applied to. We see that for certain combinations of alpha, alpha 1 and alpha 2, they are there's a bearing capacity lower than 100%, so that's the region that we are interested in. Now, let's look a little bit closer on another scale. We see, again, this is alpha going from 1 to 2, and on the y-axis, the bearing capacity for reservation with one size 0.2, and the other one is varying. It's the same graph, but a little bit more accentuated, and you will see here that's the 100%, and in this area, we must be very careful. For instance, for alpha equal to 1.6, this is the red curve, and the reservation is 0.2 by 0.2. You see that the bearing capacity of this is 103%. So you can make a hole like that, you will not touch the bearing capacity of the slab. For a hole or a reservation double this size, you will see that this is 1.6. The reservation 0.2 times 0.4, you see it's 99%. So more or less, you have not touched the bearing capacity, it's okay. And at last, you have the green curve. You see that for alpha 1.6 and B2 is equal to 0.6, you will see that the bearing capacity, you have lots of 3%. So those type of holes are okay, but when it's getting bigger, you lose bearing capacity. Let's look at it for a square slab. So alpha is 1, and we look in the function of alpha 2, which is the largest size, or which is the horizontal size, in fact, of the reservation, and we vary alpha 1 from 0 to 0.6. Doing that, you see again this phenomenon here, which is interesting for us. So for alpha 1, alpha 2 is between 0 and 0.6, and alpha 1 between 0 and 0.6. We do that because the yield lines must not come too close to the supports. We will have a demonstration just now. So this is the red curve. It's BT1 0 and alpha 2. So it means that this is a square. We can do the same for alpha equals 1.5 in function of alpha 2. And so you can study the reservation that you made. You see what reservation will be bad for your bearing capacity, and the others will not infect your bearing capacity. This is for this region. That looks like that. So you see for alpha 1.5 and dimension of the reservation is 0.2, then you see that alpha 2 between those two you should avoid. Alpha 2 between 0.3 and 0.7 A you should avoid. All the others are fine. That's the use of those graphs. And finally, for alpha equals 2, we see also here the zone where you should take care of. And to visualize it, this point for alpha equals 2, you have alpha 2.5 and alpha 2 1.3 or something like that. In between those two, it's bad. Outside that, it's okay. So we will have a graph of the bearing capacity for alpha varying from 1 to 1.5. We have seen that for larger alphas, there is never a loss of bearing capacity. So between 1 and 1.5, we have a size of reservation of 0.2, and it's in function of alpha 2. And then you have the type of lines, relationships. If we enlarge this area, which is this area is equal to that, then you see that this zone, it is you have to be careful. For instance, if you have a slab, square slab with size square slab, then you have the red curve, and you have a reservation is of 0.2 times something, and then you know if you have 0.2 times 0.1, that's the worst thing you can do. So you should at least have the size of the bearing capacity bigger than this point, because at that moment you are safe. You will have a bearing capacity which is bigger than 100. So when D1 is equal to D2, we say alpha 1 must be smaller than 0.6. Why? Because otherwise, when this is getting too small, then the yield lines will be too close to each other and are not realistic. So that's why we do not exaggerate, and we take a space of 0.2 or 0.1 times the smallest size of the slab. So for a square hole in a square slab, D1 is equal to D2, and we have then the bending moment by using the formulas of the previous slides. We fill it in and work it out, and you have this bending moment. Put it into a graph in function of alpha 1. So it's a centric hole, a square centric hole in a square slab. Then you go from alpha 1 from 0 to 0.6, and you look at the bearing capacity. Then you see something peculiar. The bearing capacity for alpha 1 equals 0. So without the hole, it's not 100%. So we can think of it as that's a mistake. But it is not, because you have a difference where M0 is defined with the yield line 30, 45, 60 rule. And the red curve is calculated with attracting yield lines. So what you see here is the difference between attracting yield lines and 30, 45, 60 rule. So take care of that. But anyway, this alpha 1 is too small. It's too close to, so we should avoid that. And then we will see that for alpha 1.1 and alpha 1.237, you will have, for instance, here 100%, and for this one you have the maximum loss, which is only 2.4%, so that's negligible. So you can say that for a square hole in a square slab, you do not have any bearing capacity. In general, when you do not want even 1% of a lot of bearing capacity, we can say that you should just avoid making holes smaller than 1/4 of the smallest slab dimension. If you do that, then you are always safe. So the smaller the reservation, the worse it gets for your bearing capacity. But the difference is not much.